3 times. So start with 2000, half it once, half it twice, half it 3 times, and you're down to what the radioactivity is going to be. So what are some examples of safety precautions you take if you're hanging around radioactive materials, and so you're being hit by this invisible energy? Get some shielding around it, limit your exposure time, wear some protective clothing, and get distance away from it. So all this is to do with the nuclear process called decay, which is where a big unstable nucleus spits out a bit of radiation. There are 3 nuclear processes. Most of what we have to know about is decay. Fission is where a unstable radioactive nucleus splits fundamentally in half. Very few radioactive nucleuses will do this. When a nucleus does split, when it does fissure, then we also get 2 or 3 more neutrons which fly out. Now, to get a nucleus to split, to fissure in the first place, we need to fire in a single neutron. But we've got 1 neutron coming in and 2 or 3 neutrons coming out. So we can then make use of these neutrons which have come out. So 1 split can then lead to 2. Well, now we can lead to 4 splits and 8 and all the rest of it, 16, 32, and you have an exponential increase in the energy, because each fission, each split releases energy, and a lot of energy. So this is how nuclear reactors work. You don't want an exponential increase in energy for nuclear reactors, you want a nice steady power output. So you get a nice steady power output of energy by absorbing some of the neutrons with control rods. And by moving the control rods up and down, you can get more or less energy coming out. All-star nuclear weapons, obviously, you don't want to be absorbing these neutrons, you want this exponential increase in energy. So with all-star fission weapons, that was how it worked. It was an uncontrolled chain reaction. The final nuclear process is called it's called fusion, and this is when 2 smaller nucleuses join together to make a bigger nucleus. Usually we're talking about 2 hydrogen nucleuses being mashed together to make a helium nucleus. It's really hard to do because the hydrogen nucleuses, or in fact any nucleus, is positive overall, and if you try and slam 2 positive things together, then they just bounce off because positive repels. So in order to mash them together, you either need a huge amount of gravity to squish them together, and this is how stars do it, or you need to have an incredible amount of heat, because heat means motion, and you need to fire these hydrogen nucleuses together really hard to make them stick. So if you want fusion to happen, you either need the type of gravity which a star will provide, or you need an immense amount of heat. Now on Earth, obviously we can't suddenly create gravity of a star, so we need to have huge amounts of heat to have fusion reactors, and that's one of the really hard things about nuclear fusion reactors. It's actually designing the materials that can withstand the heat. So what we do is we suspend this hydrogen fusing into helium in like a donut shape. They're called tokamaks, the fusion reactors. There are lots of different styles at the moment, because private companies are really getting in on the act, but the most famous type of nuclear fusion reaction is called the tokamak, and this super hot plasma is suspended in like a donut shape, so it doesn't actually touch the sides of the containers. So that's controlled nuclear fusion. Nuclear fusion happens in stars. It also happens in the most destructive type of modern nuclear weapons called hydrogen bombs. They're called hydrogen bombs because they involve hydrogen fusing into helium. So that's fusion. Motion! Woohoo! So, Newton's first law says if your forces acting on something are balanced, then the thing is going to be at rest, or it's going to be at steady speed. So when you're sat on a chair, the weight force down is balanced by the support force up on you from the chair. If you wanted to, you could work out the size of the weight force by saying W equals mg, but the forces are balanced, so you are at rest. If you're pedalling your bike at top speed, your pedaling forwards force is matched by the frictional forces acting backwards. The forces are balanced and you are at top speed. So forces balanced, you can be at rest or you can be going at steady speed. A speed time graph Steady speed is like that, obviously. Another scenario, when you jump out of an aeroplane, you get to a point where you stop speeding up, and you stop speeding up because your weight force is balanced by the upwards air resistance force. Forces are balanced, and so you're going at steady speed. The steady speed formula is distance equals speed times time. There are two types of speed, really. There's average speed and instantaneous speed. If you have a cart trundling down a ramp, then you could work out the instantaneous speed at the bottom. So this is light gates, and T1 is the time, well, in this case I'm saying that T1 is the time through the light gate, but it can have different notation. But in this case, the time through the light gate is T1, and the length of the cart thing, or the length of the card on top of the cart, is D1. So in this case, to find the instantaneous speed at that position, position 1, you'd say, well, speed is that distance divided by that time. If you wanted the average time down the whole ramp, then you'd want the whole distance divided by the whole time. And the whole time, T2, you'd use with a stopwatch because it's a much longer amount of time. Newton's second law says, well, if you've got unbalanced forces, then you're going to have an acceleration. So this would be the force diagram of a rocket, for example. If you were drawing this, you'd want the arrows to touch the object, okay? Because the SQA don't like gaps in between the object and the arrow, so that's my bad. But this is showing like a rocket taking off or whatever. So the thrust force is really big, the weight force is a bit smaller. It's an unbalanced force, so you're going to have an acceleration going up the way. Again, if you wanted to work out the weight force, you'd do W equals mg. If you've got an unbalanced force going on, if you've got an acceleration, you can use this formula Fun equals ma. So in this case, I haven't put numbers in, but in this case, the unbalanced force would be the thrust force up minus the weight is mass times the acceleration. And you might not be given the weight force outright, you might be given the mass and have to work out what the weight force is. So then you'd say T minus mg equals ma. Okay. You can, obviously accelerations can happen horizontally as well. So here's somebody where the pedaling force on the bike going forward is much bigger than the frictional force going backwards. This is an unbalanced force situation, so you can use Fun equals mass. So the pedaling force minus the frictional force is mass times the acceleration. If a person jumps out of an aeroplane and they've just got the weight force acting down on them, then that's an unbalanced force and the person will accelerate. Okay, now they won't keep accelerating forever because, as in the previous picture, after a while the drag force or the air resistance force will build up, and once the air resistance force is built up to match the weight force down, the person will fall at their maximum speed, and so their speed time graph will flatten out and look like that, and that fastest falling speed is known as terminal velocity. So somebody doing a skydive first of all experiences Newton's second law because of the unbalanced force of gravity, and then experiences Newton's first law with, as the air resistance builds up, the force is balanced, the person falls at steady speed, and that steady speed just happens to be given the name terminal velocity. They don't keep accelerating forever. So for acceleration, you've got this formula Fun equals ma, which uses acceleration. There's also the acceleration formula. Acceleration measured in meters per second squared. V is final speed, U is starting speed, and T is time. So A equals V minus U over T. The question may just give you those in like a few sentences, like the final speed of a car is this, the starting speed of a car is that, the time it takes is that, what's the acceleration, then you can just plug the numbers in. Or you may get a speed time graph and you may have to read off the values. So if you've got a speed time graph of something accelerating, in this case that would be U, that would be V, and that would be T. If you've got a speed time graph like this, so something's speeding up, the question says the car is accelerating, what distance did the car travel during this period? You think, well, it's accelerating, maybe I'll use Fun equals ma, and you'll see there's no distance in that formula, no d. So think, okay, I'm not going to use Fun equals ma. And you think, well, what's the other formula with acceleration? Well, it's A equals V minus U over T. You think, hang on, there's no d in that either. So are you stuck? Well, there's a nifty trick. If something's accelerating, then you can't use that because there's no d, and you can't use that because there's no d, and you certainly can't use distance equals speed times time because that's the constant speed formula. But what you can do is find the area under the speed time graph. The area under any speed time graph gives distance. So in this case it's a triangle, so it's base times height over 2, and there you go. That's how you find the distance if something's accelerating, because you're not allowed to use d equals vt, so you need to use that nifty trick. What are we seeing here? This is, I suppose, it's interpreting speed time graphs. So Boy Racer Bennett versus My Mighty Fiesta. Boy Racer Bennett accelerates away from some traffic lights, and in a very short amount of time reaches 60 miles an hour because his car is very rapid and it's great. My little Fiesta takes ages to reach 60 miles an hour, and so obviously you can see that the distance underneath my acceleration line, this distance is going to be much bigger than the distance it takes Bennett's car to get to 60 miles an hour. So that all makes sense. So you might have to do some interpretation of speed time graphs too, which is fine. If you drop something in a gravity field, in Earth's gravity field, then it will accelerate down at 9.8 meters per second squared, because that's the same value as the gravity field strength. And in these types of questions, we get told that there's no air resistance, so we can just assume that the acceleration is going to stay at 9.8 meters per second squared all the time. U is always going to be 0 if you drop something or throw something forward. So U is always 0, V is often what you're trying to find, which is final speed, and time is just given to you as n number of seconds. So A is 9.8 always, V is usually what you're trying to find, U is 0 always, and T is given to you in the question. Right, if you throw something forward, then you can think about vertical stuff and horizontal stuff. You usually get asked about the vertical final speed and the horizontal distance. So vertically, because we've got an acceleration, we do exactly what we've looked at there. A is 9.8, U, the starting speed, is 0 because it's been thrown perfectly horizontally. If it's thrown perfectly horizontally forward, there's no vertical speed going down the way to begin with. You want the V final vertical speed, and T is whatever, however many seconds, 3 seconds or whatever, then you can use that formula. Horizontally, there's going to be steady speed, so horizontally we use D equals VT. What people find difficult in the motion topic is the idea of vector arrows. So the best way to think about vector arrows is if you've got the Domino app, and when you order your Domino app and you order it to be delivered, then you've got this little track my Domino's screen, and there's you, and there's where your pizza is, and there's an arrow, and it's showing you how far away that pizza is and what sort of bearing that pizza is. I don't think it gives you the actual bearing, but it shows you, it puts the arrow on and shows you what direction it is in. Vector arrows often have daft names, for example displacement, velocity, acceleration and force. Well, displacement and velocity sound a bit daft, but these are the quantities which get represented by arrows, and in a sense it doesn't really matter what you're talking about. You find the length and bearing of that arrow in the same way. You do have to remember what these words are, so all very funky dogs. A stands for acceleration, V stands for velocity, F stands for force, which includes weight, and D stands for, and dog stands for displacement. So displacement means the distance with the direction, velocity means speed with the direction, acceleration and force we've met before. But no matter which type of vector arrow is being talked about, you find the length and the bearing of that vector arrow in exactly the same way. So the question will give you some sort of journey. It might be an obvious journey, it might be footering around a bit. The first thing you need to do is to draw a scale diagram. So I suppose the first thing you need to do is think of a scale. Draw a scale diagram and work out what the very start point is and what the very end point is. Because you've drawn a scale diagram, you will be able to work out the length, and then you'll be able to get your protractor and work out the bearing. So in this case, we've got the start point there, the end point there. The question's told us that dodgy bob or whatever goes along and down. You've drawn a scale diagram of it. You can then measure the length of this overall arrow from the very start to the very end. By using your scale, you can work out what that length is in real life. The bearing is from the north point and swinging round